So continuation of our module 2, which is on acids and bases and salts, would be your dissociation and your ionization constant. So when you say ionization and dissociation constant, these are actually two related terms that express almost the same meaning but are used at different occasions. So for example, when we say ionization, it refers to a type of separation wherein it can be in the form of ionization of atoms by removal of electrons or the formation of your ions. And when we say dissociation, it's the separation of a substance into smaller constituents. So very good example now would be this one, or differences. So the ionization process is a process by which atoms or molecules get a positive or a negative charge. So when you say ionization, it will always produce or form charged particles. And then when we say dissociation, dissociation is the breakdown of a substance into smaller particles such as atoms, ions, or molecules. It may form or may not form a, an electrically charged particle. Okay? So it can produce a neutral charge. So it also, for ionization, it forms ions generally. And then for dissociation, it is the formation of small constituent from larger compounds and occurs when an atom or a molecule gains or loses an electron. That's for ionization. It's because, again, it will produce or form an electrically charged uh, particle. And then for dissociation occurs with the addition of solvent and the addition of energy in the form of heat. So for ionization, it will always form ions in the end. And for dissociation, forms atoms, ions, or molecules that are smaller than the starting material. So what is now the difference between your strong acids and your weak acids, your strong base and your weak base? Okay? So the difference between those particular substances would be their ionization. So for strong acids and strong bases, they completely ionize. And when we say weak acids and weak bases, they ionize only partially. Okay? So which describes now their ionization. Okay, so let's have an example. So for example, strong acids and strong bases, we can relate its characteristic or it's similar with your electrolytes. So it can ionize completely. So for example, we have your sodium chloride in water will completely ionize into two ions together with your strong acids and your strong bases. So for example, your sodium chloride in an aqueous solution will produce an ion which is your sodium and a chloride ion. So it will completely ionize the sodium compound into sodium and a chloride ion. The same with your strong acid, your hydrochloric acid, since its characteristic is it will completely ionize, it will ionize or perform two ions, which is your hydrogen and a chloride ion. Then your sodium hydroxide will also ionize into sodium and a hydroxyl ion. So what does this mean, class? It means that whatever is the concentration of your acid or your base will also represent the concentration of each ion. So for example, if the concentration of your acid is 0.1 molar, since it will completely ionize into two ions, it means that each ion will also have a concentration of 0.01 molar. So the same with your base. If it has a zero point 0.1 molar, it means that your sodium and your hydroxyl ion will also have a concentration of zero point 0.1 molar. What about your weak acids and your weak base? So your weak acids and or your weak base. So let's have this example, a weak base, which is your acetic acid, will now form a hydronium ion and an acetate ion. So this is based from our previous theory, which is your Bronsted-Lowry. It's because an acid and a base are related to each other so that one is formed from the other by gaining or losing a proton. So that is the conjugate to one another. So they are conjugate to one another, an acid and a base. So for example, you have your acetic acid and your water. It will form now a hydronium ion and an acetate ion. So it means it has also an ionized and aionized form. So the unionized is your acetic acid and water, and your ionized would be your product. Alright? So what does this mean? So for weak acids class, its hydrogen ion will not ionize completely to form now the hydronium ion. So it will not donate all of its hydrogen to water, but there will still remain as an acetic acid in the solution. So not all will actually produce, or not all of this acetic acid will produce a hydronium ion. It will only give a portion of the acetic acid to produce this hydronium ion and an acetate ion. So what does this mean? Whatever is the concentration of your original acid will not be equal to the concentration of each ion. Right? So each ion, so they are not the same. It's only a portion. That's why they are considered weak acids and weak base. Right? Your acetic acid, that's why it's considered as a weak acid. So those are the difference between your strong acid and your strong base, together with your weak acid and your weak acid and your weak base. Their ionization, or their dissociation for strong acids and strong base, they ionize completely. For weak acid and weak base, partial dissociation or ionization only, right? So your equilibrium constant, or your ionization constant, it describes now an acid and a base. So how strong an acid, or how weak is an acid, or how strong a base, or how weak is a base. So we have three different types of equilibrium constant that we will be discussing. You have the equilibrium constant for an acid, or the acid ionization constant, the ionization base ionization constant, and water ionization constant. So if we will base our equilibrium constant from the definition of your Bronsted-Lowry. So for example, let's have the hydrochloric acid a while ago. So you have your hydrochloric acid in an aqueous solution. So which will ionize into a hydronium ion plus a chloride ion. So since this is a reversible reaction, it means that there is a forward reaction and a reverse reaction. So forward reaction is proportional to the concentration of the reactants, and your reverse reaction is proportional to the concentration of your product. So when at equilibrium, it means that your forward reaction equals your reverse reaction, and equilibrium is formed, which is now written as a constant, which is equivalent to your product over your reactant. Or we can write it this way also. If we will relate it to ionization or dissociation, this will be your ionize, and this will be your anionize. So your reactants will serve as your unionized. So they are in their original form, like your hydrochloric acid. Upon adding water, or in addition of water, or if it will react with water, it will produce now the ions, which are your hydronium ion and your chloride ion. So we can also write your equilibrium constant as ionized over unionized. Or we can also write it as your dissociated. So if we're going to relate it to dissociation, so dissociated over undissociated. Okay? So that is your equilibrium constant. So let's discuss the first equilibrium constant, which is your acid ionization constant. So your acid ionization constant, or it has a symbol of Ka. So it is an equilibrium constant for the ionization of the acid. So it represents the fraction of the original acid that has been ionized in the solution. So reflects also the strength of the acid. Alright. So ionization constant describes an acid. So the lower the Ka, the weaker the acid, and then the higher the Ka, the stronger the acid. Right? It's the opposite. So the higher the Ka, the the stronger the acid. It's because of their strong ionization. And then the lower the Ka, the weaker the acid. Right? So let's have a very good example of a weak acid. You have your acetic acid here. So acetic acid in water. So CH3 COOH plus water will now form your hydronium ion plus your acetate ion. Yeah. So your forward reaction equals now, or is proportional to the concentration of your reactant, and your reverse reaction equals the or is proportional to the concentration of your product. So at equilibrium, so it means your forward reaction equals your reverse reaction. A constant is formed wherein it is defined as, again, product over reactant, or ionized over unionized. So here, we can assume that your Ka now is equivalent to your product, which is equivalent to your hydronium ion concentration times your acetate ion. So the bracket here represents now molarity. And then you also have your product, which is your acetic acid times your water. But since water is always present in the solution, it can be disregarded. And so we will come up now with a final equation, which is equivalent to your ionized, which is equivalent to hydronium ion times your acetate ion over acetic acid. It's because, again, water is always present in the solution, and its concentration is negligible. It's because it's very small. Okay? So that is your ionization constant of the acid, or a weak acid. So Ka is equivalent to your ionized over your unionized, or product over reactant, or undissociated, dissociated over undissociated. Okay? So that's your ionization constant of the acid, or acid ionization constant. So what we have to remember here is a large Ka value indicates a strong acid. It's because it means that acid is largely dissociated into its ion. It's because of complete ionization. And then a small Ka value means little, or little of the acid dissociates or ionizes. So we have now a weak acid. So it describes now a strong acid from a weak acid. So how much is being ionized? So it represents now the ionization of the acid. So how much is it completely or is it partially only? So if it's completely ionized or if it has a higher Ka or large Ka, it means it is a strong acid. And then if it will have a small Ka, it means a portion only of the acid was ionized or dissociated. That's why it's considered as a weak acid, or it means that it can only measure a certain amount or concentration of the hydronium ion. That's your acid ionization constant. Next would be your base ionization constant. So the same class, for example, if we will have now acetate ion, which is considered as a base. So if we will have that example in water, will also produce now its product or the ionized form, an acetic acid plus your hydroxyl ion. Okay? So this will be your product and this will be your reactant and this will be your product, or this is your unionized and then this will be your ionized. Right? So your water here will serve as an acid. It will donate its proton to the acetate ion to produce now the conjugate acid, which is your acetic acid, and a conjugate base, which is your hydroxyl ion. So after water donates its hydrogen, it will produce the conjugate base. So how will we now understand the ionization constant of the base? So Kb, the same with your Ka, measures now the equilibrium constant for the ionization of your base. It represents the fraction of the original base that has been ionized in the solution. So it reflects the strength of your base. So Kb now, so if at equilibrium, if the forward reaction equals the reverse reaction, we can assume that your ionization constant or the constant of the base is equivalent to the product over the reactant, or it is equivalent also to ionized over unionized. So it will become now acetic acid, which is a conjugate acid here, and a hydroxyl ion. Again, the bracket represents molarity, so moles per liter, and your base, which is your acetate ion. Okay, so we can remove now water. It's because it's always present in the reaction. It is disregarded or it is negligible because its concentration is very, very small. Right? That's why we can remove it in the equation. So the general equation for the base ionization constant would be product over reactant, or ionize over unionized. Okay? Yeah. So what is now the meaning of this one? So for the Kb, a large Kb now value indicates a strong base. So because it means that the base is largely dissociated into its ions, and then a small Kb value means a little of the base dissociates. So you have now a weak base. So the same with our acid, Kb is used for describing a strong base with a weak base. So if it will have a large Kb, so it will completely ionize or dissociate, which pertains now to strong bases. And for small kb, so it means partial dissociation or only, or ionization. It means that a portion only of the original base was ionized, which describes now a weak base. Alright? So that is now your base ionization constant. So this is your base ionization constant. Next would be your water ionization constant, or it is represented by your Kw. So your Kw, it is related to your Ka and your Kb. Alright, so let's have the formula a while ago. Let's combine that one. So let's prove that Kw, so it is the ionization constant of the water. So Kw is equivalent to Ka times Kb, or it is also equivalent to your hydronium ion plus times your hydroxyl ion. So at 25 degrees Celsius, it is equivalent to 1 times 10 raised to negative 14. Okay? So let's prove that Kw is actually equivalent to your Ka and your Kb also. Alright? So let's have this one first. So let's combine our Ka and our Kb a while ago. So our Ka kanina or a while ago is equivalent to our hydronium ion concentration times our acetate ion. And over now acetic acid. What about our Kb? So Kb is equivalent now to acetic acid times a hydroxyl ion over the acetate ion. So this should have a product of hydronium ion times hydroxyl ion. So Ka times Kb is also equivalent to these two particular equation. So this one and this side. So let's try to combine or remove similar terms from both sides. So you have now an acetic acid on this side. So remove this one and an acetic acid on this side, which is found on the numerator. So cancel. You also have an acetate ion that is found on the numerator of this side. And you also have an acetate ion that is found on the right side, which is found on the denominator. So remove those one. What's left now is your hydronium ion concentration and your hydroxyl ion concentration. So this means that your Ka times Kb is also equivalent to your Kw. So Kw, or water ionization constant, is equivalent to Ka times Kb, or hydronium ion times your hydroxyl ion. Alright? So there's another method to prove this one, which is this one. So let's have the equation a while ago. So you have acetic acid plus water. It will produce a hydronium ion plus an acetate. Yan. And then the other equation for the conjugate base, which is your acetate. So acetic acid is the conjugate an acid, and your conjugate base is your acetate. COO plus water, it will produce now the acetic acid plus your hydroxyl ion concentration. So if we will get the net total of this reaction, so let's try to remove the same uh, compounds. So for example, your acetic acid is found at the left side of this one, and then it is also found at the right side of the other equation, so we can remove that one. Your acetate also is found at the left side of the second reaction, and it is also found at the right side of the first reaction, so we can remove that one. So what's left is you have two molecules of water, so H2O plus H2O, which is also now which will also produce now a hydronium ion plus a hydroxyl ion. So it means that water also is between a hydroxyl ion concentration and a hydronium ion concentration. So based from autoprotolysis of your water, or based from its amphoteric and amphiprotic characteristic, your Kw is also equivalent to your hydronium ion and a hydroxyl ion. Okay? So please remember that one. So Kw is equivalent to 1 times 10 raised to negative 14 at 25 degrees Celsius. Okay? So those are your different ionization constants. Let's have the relationship of the ionization constant with your pH and your pOH. So the degree of acidity or basicity of a solution can be defined in terms of molar concentration of hydronium ion and hydroxyl ion, or Ka and Kb, or the pH value system by the Sorensen equation, where pH is the logarithm of the reciprocal of the hydronium ion. So whenever you see actually a symbol which stands for P, letter P, it means that it is the negative log of a certain concentration. Right? So whenever you see a symbol which has AP, it means it is a negative logarithm of a molar concentration. Okay? So pH is equivalent to the negative log of your hydronium ion. So it measures now the acidity. So the higher the hydronium ion concentration, the more acidic. Okay? Or if you want to determine now the hydronium ion, the opposite now, if the pH is given, so it is just the anti-log negative pH. So you can actually use your calculator, your scientific calculator, for computing this one. And then measurement of a base, so pOH, so it is the negative log of the hydroxyl ion. And then you can compute also for the hydroxyl ion if your pOH is given. So it is the opposite. It is the anti-log negative pOH. So pH, the higher the concentration of the hydronium ion, the lower the pH, the more acidic. And then the higher the hydroxyl ion, the lower the pOH, and then the lower the pOH, the 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 lower the pOH, the more basic is the solution, or the higher the pH. Right, that's your pOH. And then pKa is also the negative log of your Ka. So this is related to your ionization constant, your Ka. Your pKa bears exactly the same relation to your Ka as pH does to its hydrogen ion concentration. So it is also a measure of the acidity of a certain substance. Right? Yeah. So it is the index to express acidity for weak acid. So the lower the value of the pKa, the stronger the acid. So please remember that one. So the lower the value of the pKa, the stronger the acid. So pKa is just the negative log of your Ka. So, and then if you want to convert your pKa to Ka, you can use the formula anti-log negative pKa. And then pKb is a negative log of your Kb. So again, the same with your Ka and your pKa. Your pKb is also a measure of the basicity of a particular substance. So it is an index to express basicity or alkalinity for weak bases. So the lower the value of the pKb, the stronger the base. So that's for your pKb. So in difference now with your pKa, the lower the value of the pKa, the stronger the acid. And then for pKb, the lower the value of the pKb, the stronger the base. And then the relationship between your pH and your pOH is derived from the formula of your pKw, since it is between your hydronium ion concentration and your hydroxyl ion concentration. If you will make the value of your hydronium ion and your hydroxyl ion concentration into a bigger value, that's your pH and your pOH. The same with your Ka and your Kb. So if you will make it bigger, it is also your pKa and your pKb. So you can determine or convert pKa to pKb, Ka to Kb, or vice versa. You can convert pKb, you can convert pKb to pKa or pKa to pKb, and then Kb to Ka. If you will use this formula, the same with your pH. So if pH is given, you can determine pH or vice versa. If pH is given and you want to determine pH, you can use the formula. And then you can also determine the hydroxyl ion if the hydronium ion is given, or vice versa. You can determine the hydronium ion if the hydroxyl ion is given. So for example, this one. So for pKw, it is equivalent to 14, and its Kw is also equivalent to 1 times 10 raised to negative 14. So for example, you want to determine the, let's have the acetic acid again. So acetic acid, for example, in water will produce now a hydronium ion plus an acetate ion, right? So if you know now the pKa of your acetic acid, you can actually determine also its pKb, or the equivalent pKb of your conjugate base. So by using this formula, so pKb is equivalent now to pKw minus your pKa, or vice versa. If you want to determine the pKa, if the pKb is given, you will use this formula, pKw minus your pKb. And the same if your Ka is given, if you want to determine the Kb, for example, you can use this formula. So Kw over Ka. So these are derived from these two formulas. And if you want to determine the Ka, if Kb is given, you can use this formula, Kw over Kb. So it is used for converting whichever is missing. The same with your pH. So pH, if for example you want to determine the pH of a base, if its pOH is given, you can have this one. So pH is equivalent to pKw minus pOH. And then the same, if you want to determine the pOH, if the pH is given, it will become now pKw minus pH. Yeah, so this is derived from this formula. And then if you want to determine the hydrogen ion concentration of a particular substance using its, if we want to determine the hydronium ion of a particular substance using its, the hydronium ion of hydroxyl ion of the conjugate base, you can use this formula. So this one, the Kw times hydronium ion times hydroxyl ion. So for example, you want to determine the the hydronium ion of a base, or an acid, if its hydroxyl ion is given, you can use this formula. So hydronium ion is equivalent to Kw over hydroxyl ion. So the same with your hydroxyl ion, if you want to determine now its hydroxyl ion, if the hydronium ion is given, you can use this formula. Kw is equivalent to hydronium ion. So those are the relationship between your pH, your pOH, and your pKw, the same with your Kw and your hydronium ion and your hydroxyl ion, and your pKw with your pKa and your pKb. And then the same also with your Kw and your Ka and your Kb.